This paper demonstrates how to lift a well or initiate a well after a shut-in have been commenced using transient wellbore simulator that's integrated with the reservoir near wellbore model. Whenever a well is shut in, a phase segregation is expected. And whenever the different phases segregate, different fluids will accumulate in different sections of the well. This will increase the bottom hole pressure and increase the wellhead pressure as well. However, some wells may not start again after the shut-in have been commenced. Those types of wells are known as lazy wells. In this paper, we will deal with a case that's a lazy well and how we can initiate it using only gas injection at the wellhead without using cold tubing methods. For a well to be lazy, there are different behaviors it might expect it before being lazy, or a combination of behaviors. The well might be high on water production, plus there might be a depletion inside the reservoir. Sometimes short shut-ins might contribute to lazy wells. Another reason it might be is a damaged near well or a bad petrophysical properties. Additionally, as production proceeds over time, a reduction in the produced fluid properties might contribute to this behavior as well. To model a lazy well, it's necessary to do three parts of the model, which is fluid model, wellbore mechanic model, and the reservoir model. For the fluid properties for the well under study, the well is actually as a conventional back oil with a oil density API of 35 degrees. Plus the water cut is very high on this well. It actually reaches somewhere between 46 and 47%, with a associated gas specific gravity of 0.63, and the saturation pressure is 2900 psi gauge. The fluid has been modeled using correlations, since it's a conventional black oil model. For the production system, a wellbore is modeled using Olga software, and different casing sizes and different tubing sizes have been input inside the software. And the key characteristics of wellbore mechanics are this is a packerless tubing installation, a production liner of 4.5 inches OD with a production tubing of 3.5 inches OD with ID of 2.9. The mid depth of the perforated interval is 3,300 meters. Additionally, there is a choke installed on the wellhead, which is opened regularly at 32 of 64th of an inch. Again, Olga HD model is used to simulate the flow from the well. And for the final part of the production model, a numerical reservoir model is used. A 3D model is created by a companion software which is called RockX. This 3D model is of height of 85 meter thick, which is the pay zone thickness, and it's divided into two layers. The bottommost layer is the a strong aquifer, and the topmost layer is the production layer. The initial reservoir pressure of the reservoir under study is 4,500 psi gauge, and the reservoir temperature is 212 Fahrenheit, and the average porosity is 17%. The well logs and near well cased hole logs shows a water saturation of 45%. The transient model could be initiated by entering the boundary conditions, which are represented by PWFs if available. Additionally, any static shut-in surveys, which are pressure surveys that are have been taken in the field. Additionally, wellhead pressures should be entered for the model to be initiated. Once the model is initiated and it's open for production, we use a steady-state steady-state approach to calculate some parameters, which are the oil rate, water rate, and bottom hole flowing pressure. Actually, we have matched the data for three choke sizes, which are 84 and 48 and 120 of 64th of an inch. The results are consistent and shows a good match between the calculated and the measured data. Those measured data are actually measured using PLT surveys. Additionally, the plot below shows the transient behavior inside the wellbore simulator once the production actually starts. Actually, it shows the production starts to stabilize after 1 hour of each choke size increment or decrement. It's very necessary to evaluate the transient behavior of a well whenever it's shut in. This actually provides very valuable information. For example, we can determine where the gas liquid contacts actually is placed inside the well. Additionally, it shows us the pressure and temperature distribution inside a well or any given point of interest. Using the shut-in keyword inside the wellbore reservoir simulator, actually it was determined that there is a need of a minimum of 30 hours of shut-in for this well to start properly. Sudden shut-in actually is preferred over gradual shut-in. This actually showed a more gas content inside the oil column. Additionally, the water leg was found to be somewhere of 1,200 meters long. Actually, some of the water have been re-injected inside the reservoir. Next step actually will be is to test the model after shutting it. First, we start by producing the well naturally by Binup strategy, which change in reservoir pressure actually presents a great challenge on the Binup strategy. It's very evident from the simulation results. Any pressure drop inside the reservoir, it will actually reduces the maximum bean size. We can see in the table the maximum bean size have been reduced from 48 for the reservoir pressure of 4,500 up down to 8 of 64th of an inch in the case of reservoir pressure of 4,350. So this is something to consider and watch for while using this method. Direct gas injection at the wellhead is not a new approach. However, it can save time and save cost whenever it can be applicable. However, it requires some conditions to be applied. For example, packerless completion is the only candidate for this lifting method. This lifting method actually is perfect for the failed attempts to start up a well before doing any cold tubing procedures. And once it applies successfully, it can save cost and time. However, it requires a rigorous calculations and some precise determination of the optimal injection rates. We have started the well after 120 hours of shut-in. The well started successfully. However, after 1 hour or less than 1 hour, actually the production ceased, and it started to show some slugging behavior until the production flattens out. So we'll try to directly inject the gas to this well after changing some modeling parameters in the Olga model. Many injection rate has been assumed or has been input to the software, and it ranges from 0.25 kilogram per second up to 5 kilogram per second. The optimal operating envelope or optimal injection envelope for this well was found out to be somewhere between 0.75 up to 2 kilogram per second. However, the most optimum injection rate was found to be 1 kilogram per second. After determining the optimum injection rate, it was necessary to take a closer inspection of other lower and higher end of rates. For example, it was found out there are some problems we can run into once if we chose lower injection rates. The main issue will be is the slugging behavior that will result. For example, in this plot, the well unloads after 8 hours almost. After starting to unload, there is a clear pattern of slugging that's happening inside the well. Also, upon closer inspection, high surge volumes was calculated in the surface facilities, so this is something to watch out for if smaller rates were to be selected. Next step will be to determine the optimum injection duration. Many injection duration have been parametrically input inside the software, and it was found out a minimum of 1 hour of continuous injection is required to unload the well whenever you are using a parameter of 1 kilogram per second of injection rate. Concerning the production choke opening, actually it's preferred for the production choke to be fully open whilst displacing the fluid inside the wellbore. However, it's recommended to decrease the choke size whenever you are using smaller injection rates to reduce the slugging and instability behavior inside the wellbore. Displacement efficiency actually was found out to be very good inside the well. Most of the annular space fluid was displaced. However, a maximum of 5% of liquid holdup was observed inside the annular space. After the time passed by and the continuous injection was commenced, a very thin liquid film was observed in the inner wall of the casing. However, it was noticed that lower injection rate actually provides a much greater and much stabler displacement. For example, we have in this plot the black line representing 0.25 kilogram per second, and the purple line represents 3 kilogram per second injection rate. It's very clear that displacement efficiency of the black line is much better than the purple line by a relatively small margin. To fully evaluate the displacement efficiency, actually it's recommended to use a more advanced modeling approaches using the computational fluid dynamics. Thanks for your valuable time.